Okay, topic 10.2, we need to look at the chemistry behind some of these organic molecules, and that chemistry of the homologous series is largely determined by the functional groups that they contain. So that's what we're going to look at. You can see all the different families that we're going to be going through. And we'll start with the alkanes. Now, alkanes are pretty unreactive because the bonds are CC-CH, they're pretty nonpolar, particularly the CC bonds, and they are strong. Right? We can burn them. If we burn them, we're going to get carbon dioxide and water. We can test for those products using lime water and cobalt chloride paper. And if we're not getting enough oxygen there, we're likely to see some soot forming and some of that odorless, poisonous, colourless carbon monoxide. So it's important that chimneys and flues at home are clear and there's enough oxygen getting in. The one reaction that we do need to know about is free radical substitution. And if we take our alkane, add in some halogen and expose it to UV light, we can end up with a variety of products. And the process is the UV light causes a homolytic fission within the halogen. So you can see my single-headed arrows showing that one electron, two electrons in that bond, that shared pair, one electron goes with each atom when it breaks, and we end up with this radical. And a radical is just something with an unpaired electron. So that radical can then go on and react with the alkane, and a propagation step is any step that produces more radicals. So there's going to be a few possibilities here, and then again more possibilities for termination. Termination is where two radicals combine to produce no more radicals, and so we end up with a variety of products. Alkenes, a little bit more interesting because we've got this pi bond here. So in there's a pi and a sigma bond. The pi bond can break to form two new strong sigma bonds, so it's energetically favorable. This is an addition reaction. We're adding across the double bond to produce one product, and we'd actually call it an electrophilic addition because this is an electrophile. It's seeking out a negative rich area. So our alkenes will undergo addition reactions, and we can identify unsaturation, which is this double or triple bond. Triple bonds would be alkynes, but we identify that unsaturation by adding in bromine water. Bromine water, you can see here, we get the dibromo compound. It just adds across in two spots, and the bromine water goes from orangey brown to colourless. So we could also, as you see in the example here, we can add hydrogen halides. With the help of some phosphoric acid, we can add water across to make an alcohol. And if we use a nickel catalyst, we can hydrogenate it back to an alkane, which is important for margarine production. One big industry for alkenes is polymerization. So addition polymers are made kind of just by adding together alkenes. So if we have catalysts present, high temperature, high pressure, we can form these long chain molecules. And some examples and uses of very familiar plastics are listed here. And we start from our monomer, which is our basic building block. And by knowing the name of the monomer, it's pretty easy to work out the name of the polymer because we just put the word poly in front of it. You can see there a representation for the chain. Now, we just have to be a little bit careful if we're trying to draw out what the long chain looks like. If we take propene as an example and polymerize that up to polypropene, I can see that looking at my monomer, every second carbon needs to have a CH3 on it. So the chain continues like that. Very often students put that inside the chain, and that's not the right place for it. So these different groups will give me different properties of the polymer. Alcohols undergo oxidation and nucleophilic substitution reactions, or more commonly known as esterification. But before we get on to the oxidation, one thing we can do is simply burn an alcohol. That's probably something you've done as part of your energetics studies, and quite nice clean burning fuel. It's already partially oxidized, and we end up with carbon dioxide and water produced. Now if we're oxidizing them chemically, two reagents we've got, we can use acidified potassium dichromate, we can use acidified potassium permanganate, and certainly this one, we get a nice characteristic color change from orange to green as the state of the chromium changes. This of course starts off purple, it won't be purple at the end of the experiment, but it shows you that a change has taken place. So if we think back to these definitions of primary, secondary, tertiary, they react slightly differently when we oxidize them. Primary alcohol, so one where that carbon is attached to two or more H's, will be oxidized, there's our oxidizing agents, to produce an aldehyde, and then further oxidized to produce a carboxylic acid. Secondary ones, where there is just one H attached to the carbon that's attached to the OH, will give us a ketone, and tertiary won't react at all. So by using this stuff and looking for color changes, it would be a way of seeing whether we had primary, secondary or tertiary. We could distinguish whether one of these was present because it wouldn't give a color change. So if we want to trap the process at this aldehyde, we would need to set up a distillation apparatus. So because this has weaker intermolecular forces than the alcohol, as soon as it's formed, it's going to be vaporized and we can condense it down here and we end up trapping just the aldehyde. If we wanted to go right through to the carboxylic acid, we'd have to use a reflux setup, and reflux allows us to heat together organic chemicals. We've got a condenser above, and it means all the volatile stuff condenses back into the mix and it gets fully oxidized right through to the carboxylic acid. The last one there, forming esters. Esters, very pleasant smelling compounds, often used in flavorings, perfumes, and we're reacting together carboxylic acid and an alcohol, and as described as you see there, nucleophilic substitution. So we are essentially adding this here, is going in there and taking the place of that bit. And we use some concentrated sulfuric acid as a catalyst for that reaction. And you can see here our ester link. Well, I guess we should maybe have that C included to show that it's an ester rather than a carboxylic acid. And naming it, you can think of what the parent compounds were. So we're starting from methanol, so there's my methyl group, and ethanoic acid, there's my ethanoate. An example you've maybe come across that will help you remember what to do is when we reacted ethanoic acid, which looks like that, with sodium hydroxide, we ended up with this salt, and we called that sodium ethanoate. So hopefully you can see why this is called methyl ethanoate. Right, halogenoalkanes, they can undergo what's called nucleophilic substitution. Again, swapping something in, so this is my nucleophile, an electron-rich species with a lone pair attacking in at that carbon. You see my arrows coming from that lone pair because that's what's going to be making the new bond. And it kicks out the Cl. Now we don't need to know the mechanism at the moment, but hopefully you can see that it's taken its place and substituted for it. And the reason it reacts like this is because we've got a polar bond. Cl's more electronegative than the C, and so this is susceptible to nucleophilic attack. Nearly there, I think. Benzene, we heard in the last section that because it was delocalized system, it was going to prefer to do substitution reactions over addition, and you can see here generation of an electrophile, two different electrophiles being produced by the reactant mix, and then my benzene ring substitutes them in for one of the H's that was attached to it. So I've maintained my delocalized structure at the end. Great, that is it.